This conference will now be recorded.
Hey, I'd like to welcome everybody. It's sort of a belated Happy New Year, as this is our first 2022 webinar under the UG2. So look forward to many more. I'll talk a little bit more about that in closing, but just want to again welcome everybody and thanks for spending some time to come in. Before our sort of main event here, just some quick administrative updates. Rudy, if you could go to the next slide. Here's our agenda. So we'll do the some quick administrative updates, and then we'll have the main presentation, and then we'll do a quick wrap up. Next slide. Just this is just for reference. You can download this later for the new folks if they want to see who's on the UG2 steering committee. Next slide, please. Okay, so the big update that really I want to just spend on time is the 2022 glider workshop. A steering group for the workshop has been stood up, and they've met several times, and we'll continue to meet monthly, and that will increase in time as we get closer. But so yesterday the group met and they agreed on some tentative dates and location. And I say tentative just as we need to clear this through the UG2 steering committee yet and work a couple of logistics just to make sure that all that works out. But as you can see here on the slide, the venue would be at the University of Washington in Seattle, hosted in their NHS hall there, the Northwest Horticultural Society, which is in their Botanic Gardens. Again, that date, the tentative dates I'd like folks to kind of pencil into their calendars is the 20th through 22nd of September this year. We're planning on a 2.5-day event. So this is scheduled Tuesday, Wednesday, Thursday. So it leaves the Monday, Friday for travel. And we'll be calling on abstracts. I'll talk a little bit more about that in a second. And you can see what the goals are, which always are for the UG2 to share research, ops, and development accomplishments across the community and refine and build on deliverables that came out of the 2017 and 19 workshops that we'll be sharing in the near future. Next slide. So this, we'll be talking about sending out abstracts. We'll send out an abstract call against this sort of conceptual framework, and we'll see where the concentration on the responses are to formulate an agenda, and including plenary sessions and speakers. So really, that response will drive that agenda. So you, the group, will be driving this event and how we set it up. So, and these are just sort of the concentration areas as we send the abstracts out. So please we're probably a few weeks out before being able to send this the abstract call out, just to clear some of the logistics to make sure everything's good on that end. But please pencil that in your calendar and look forward to getting some responses from the folks. Yeah, always please encourage folks, any of your colleagues, any friends, anybody, to join UG2 and go to the website, and you can do that. Next slide. Okay, so I'm excited today. I mean, we have a great for the group of subject matter experts that led the glider efforts for the 2021 hurricane season. This was a IUS-led effort across 4 regional associations and truly a collaborative effort, including NOAA, Navy, academia, and industry, with the ultimate goal to inform the ocean models of the physical conditions that ultimately impact hurricane intensity forecasts through the ocean atmosphere coupled models. So again, we'll introduce folks as we go along, but a great crew of folks, as you can see here. And we'll start off with the overview on the next slide with Kathy Bailey, who actually was the project lead throughout the entire hurricane season. So I guess we'll go to the next slide and turn it over to you, Kathy.
Great, thank you. As mentioned, I'm Kathy Bailey. I'm the Underwater Glider Program Manager at IUS, and I just want to also thank Bill and COL for organizing this topic today and giving us the opportunity to discuss the Hurricane Glider Project and the activities from this past season with you all. So as mentioned, I'll give a quick overview and then I'll hand it off to the regional reps and all to their talks from here. Next slide, please. So as you're all aware, hurricanes are incredibly damaging to the US. And since 1990, we've seen improvements to hurricane track forecasts at NOAA, but the intensity forecast improvements have been marginal. Next slide, please. So the ocean, of course, plays a significant role in modulating hurricane intensity, and its essential ocean features like the loop current and the Gulf Stream and subsurface warm and cold pools and freshwater salinity barrier layers have been linked to rapid intensification and weakening. So to improve the intensity forecast, we really need to represent these features well in the models. However, they're challenging for the models because they're highly dynamic in nature, and we have very limited subsurface observations, especially below 10 meters, that are available to initialize the models. So overall, our goal here is to accurately represent the upper ocean in the models by capturing these features throughout the entire hurricane season. And gliders, of course, are uniquely suited to help since we can steer them into these specific features. I do want to emphasize we're not chasing storms with gliders. Instead, they're intended for long-term sustained monitoring throughout the season in targeted areas to capture those dynamic features and to help keep the ocean models on track. Next slide, please. So represented here is a snapshot of the entire glider, the glider missions over the entire hurricane season. In blue, we have the hurricane glider missions that were operated by NOAA and the IU's partners. In green, there are partner gliders with missions that were not hurricane focused, but whose data are shared and therefore leveraged through the IU's Glider Data Assembly Center. And then in yellow, we have US Navy gliders that were contributed as part of a NOAA Navy collaboration that's been ongoing for the past, almost 4 years, I think now. So this is where the IU's RA partners deploy and recover the gliders, but the Navy owns and pilots them based on waypoints that we provide them. So the logistics for the collaboration this year was supported by NOAA's Office of Marine and Aviation Operations Uncrewed Systems Ops Center. So I just want to give a shout out to them. And that support was really critical this year, especially in the Gulf of Mexico region, as you can probably tell with the heavily yellowed lines there. And then in pink, I show 30-day snippets of sail drone tracks. Sail drones were up there through an OAR-led project to measure air-sea fluxes in and near tropical cyclones. And when they weren't pursuing an active storm, we were able to do a co-location exercise with the gliders, and you'll hear more about that in the following talks. As the upper right graphic shows, we had the most days at sea to date by the red line, and we had fewer shallow water gliders this year, which meant fewer profiles compared to last year as well. Next slide, please. So here are some metrics that were gleaned from the glider DAC. We had 79 missions total, as shown in that map, that contributed data. With an 82% success rate loosely determined by roughly 15 days at sea. I'll be honest, I looked through every mission and got intel from everyone, the operators, and understood of the 79, the failures were mainly due to CTD pump issues or a leak, or in one case, a lost glider or a shark attack. So this was actually a pretty good metric. I think generally speaking, though, we want to refine the metric for success by region and hone that number a little more. But 82% success is a pretty good number. Of the 79 missions, 44 were hurricane gliders and collected over 2,000 days at sea. We had over 100,000 temperature and salinity profiles submitted to the GTS via the IU's Glider DAC. And the Weather Service National Data Buoy Center plays a central role in helping us get our non-federal partner data through NOAA for assimilation into the models. We also had over 15 institutions as part of this effort providing data. Next slide, please. So in terms of those institutions, one of the biggest highlights, as Bill alluded to earlier, is the collaborations and the partnerships that make this entire multi-year effort possible. And it's really been growing over the years too. I think in 2014, it started with just a few partners, AMOL and Rutgers, and I think CARICOOS, and it's really expanded over the years to include all these different institutions. And I think it continues to expand too. So the great thing about this is the training and the knowledge exchange over the years that have even helped us overcome challenges created by the COVID-19 pandemic. And another thing I want to highlight is that the academic partners have also actively engaged students and provided them the opportunity to join in deployments and recoveries and some of the technical work. So it's great to see them inspiring our young oceanographers and engineers. Next slide, please. All right, so I'll give some quick highlights. Many of these will be discussed in more detail in the following talks. But the biggest thing this season was that this was the first hurricane season in which the glider temperature and salinity profiles were assimilated into the operational global real-time ocean forecast system. And there was an upgrade last December 2020 that introduced DA into that operational model for the first time. And so this was the first season in which we got to see the results of that. And Scott Glenn is going to go into a bit more detail. I think it's Scott speaking in his talk. And this was also the most successful season we've had to date with the NOAA Navy collaboration. And you'll hear in the regional talks a lot of reference to those activities as well. But overall, we had 14 missions, 80% success rate. And then the next couple bullets are again going to be discussed, but the first is in reference to a piloting exercise with the Navy where we sent a glider from the Gulf of Mexico to monitor the loop current, and then it went down through the Florida Straits and caught up with the Gulf Stream for recovery near South Carolina. So that was a successful cross-regional collaboration. And then the next, as I mentioned earlier, is our first effort to co-locate surface and subsurface autonomous vehicles, measuring ocean obs simultaneously for the first time from uncrewed systems. And the glider partners are also contributing to a broader NOAA effort led by GOMO. And GOMO stood up a task team that connects ocean observing activities to research on air-sea fluxes with the goal of improving hurricane intensity forecasts. So we're all working together to contribute to that broader effort. And then, of course, we had glider data in proximity to 8 tropical cyclones this season. The most important was a glider during within the Gulf of Mexico, a Navy glider that was monitoring the Gulf during Hurricane Ida. And then next slide, please. So not to end on a low note, but I do want to give some insight into some of the challenges we face. And some of these are probably familiar to the UG2 community as well. Like most things, I imagine, this is an underfunded effort. It relies heavily on annual increments of disaster supplemental dollars, although it has some IU's core funding as well and AOML and GOMO funding attached to it. But these supplementals that help drive our activities aren't predictable or guaranteed, and they last 1 or 2 years and then they're gone. So every year we're dealing with high levels of funding uncertainty, which of course affects long-term systematic planning. And the funding cycle itself is a challenge. Our funds are mostly issued through grants, which of course makes it difficult to sync up when the funding is received with when we can get the gliders deployed. So early hurricane season deployments have been challenging as a result of that. Recap is a growing issue. We have an aging fleet across the board. The infrastructure bill will hopefully help with some of that, but it's certainly not going to be the degree that is necessary for ensuring our entire fleet is up to speed. Major issue with bottlenecks, manufacturer bottlenecks for servicing and calibration of equipment. And I understand, again, this is sort of a more broader UG2 community challenge that we're all facing, in part obviously due to COVID supply chain issues, but these bottlenecks have been seriously impacting our deployment planning. So maybe, UG2 could possibly be an avenue to help us push manufacturers to stay on schedule and deliver gliders within reasonable timeframes. And the last couple, well, I think, so in reference to that image there, I guess I really want to show that as an illustration of the impacts of some of these challenges I just mentioned. We had the Gulf of Mexico was barely covered going into peak hurricane season. And again, if that Navy glider wasn't there monitoring, we wouldn't have captured the ocean conditions during Ida's approach. So I just highlight that as a sort of an illustration of the impacts of those issues and the real high need to help resolve those issues. The last couple of bullets here are really in reference to our need for a closer connection to NOAA's modeling center and the hurricane center groups so that we can adjust our deployment strategy to maximize the benefit and impacts to the models. So for the sake of time, I'll end there. But we're currently beginning the deployment planning for 2022 hurricane season, and of course facing funding challenges related to that, but we'll see what we can do. But I will hand it over then to the next speaker. Thanks so much.
Okay, well, if you want to start dropping questions into the chat as we go along, and we can address them at the end, appreciate it. For next, we'll be moving to the Gulf of Mexico, and Dr. Kerri Whilden from Texas A&M has the lead, and you can see Kevin Martin and Stephen Howden and Chad Lemke were big contributors to this effort as well. Kerri, all yours. Thank you.
Thanks. Very happy to be giving the update for the Gulf of Mexico. So thanks for having me. Next slide, please. So to give an overview on some of the highlights over the last hurricane season in the Gulf of Mexico, 8 storms made landfall in the United States last hurricane season. And of those 8, 6 of them were in a Gulf state. So a very active season, another very active season in the Gulf of Mexico. One, as Kathy mentioned, was Hurricane Ida, which was a major hurricane at a Category 4. We also had 2 Category 1 storms and 3 tropical storms. Not included in the 6 that hit a Gulf state, but is worth mentioning is Hurricane Grace, which made landfall near Veracruz, Mexico, but did have a potential landing in Texas, and as it traversed the Gulf, ultimately landed in Mexico. So still important to have those measurements in the Gulf of Mexico to help for the intensification and trajectory associated with that. Another highlight, not glider related, but still for profiling data, is the temporary increased cycling of Argo. So during peak season, they transitioned some of the floats for Argo to 2-day cycling rather than the normal approximately 10-day cycling for profile measurements to the getting the profile measurements in real time. 14 gliders were deployed last hurricane season, and the picture to the right shows some of the trajectories that were after peak season. So thanks, Kathy, for mentioning and showing some of the challenges that we faced last year. The majority leading up to peak season, we really just had 1 glider that was taking measurements offshore, and we were very lucky to have that in position for having measurements ahead of Hurricane Ida. 2 of the glider missions that we had out were funded by Shell, and they were earlier in the season, before peak season. The majority of our profiles and our glider efforts were from the Navy, and that's 6 out of the 14 that we had out there. We had a lot of very successful Navy missions, which I'll talk about on the next slide. Multiple over 100 days, and that ended up being the majority of our total number of glider days in the Gulf as well. We also had leverage partner data sets that weren't specifically focused on hurricane intensity, but did provide data towards the overall effort for profiles, and those were from USF and MOTE. Next slide, please. So again, just to highlight some of the successes that we had for the Navy gliders later in the season. You can see 4 profiling Navy gliders with nice triangles in the northwestern Gulf of Mexico, and as of earlier this year, they were approaching 100 days. They were recovered later in January, and I believe the final count was near 120 days. The other mission that we had going on around that time was what we had dubbed the experimental glider mission, and it was a cross-regional, multi-institution collaboration where we did deploy a glider off the coast of Louisiana, and it went through the loop current and through the Florida Strait. So if we go to the next slide, we'll have a better highlight of that trajectory. Wonderful. So as I mentioned, deployed off the coast of Louisiana. It went down and around one of the loop current eddies, or the pinching point, where it was kind of, is it an eddy? Is it still connected? Is it going back and forth? So it was good to have a glider going in and around that boundary. Then it crossed, it entered into the loop current down through the Florida Strait, and then was recovered up through, it went through the Gulf Stream and was recovered off of South Carolina. There were a lot of great things that happened as part of this mission, and really working close with the Navy and using their automatic piloting tool, Ghost, to help with the waypoints, to determine where the glider was going to go over the course of the deployment, and just working with the different regions in order to make all of this coordination and logistics happen. Next slide, please. I think that's it.
Thanks, Kerri. Thank you very much. Great effort there. So we'll move into the Southern Atlantic here, and we have Dr. Catherine Edwards from Skidaway Institute of Oceanography, and also worked very closely with USF, Chad Lemke there, and Dr. Robert Todd at HUI. Catherine, turn it over to you.
Thanks, Bill. So yeah, this is a large team in the Southeast Atlantic. SECOORA-funded scientists include groups from UNC Chapel Hill and Georgia Tech. I think altogether the group of us working in the SAB was about 15 of us strong. Next slide, please. So a bit of an overview of our missions. They fell into 3 different categories. The first were funded through the Southeastern Atlantic Regional Association, SECOORA. And so our focus in SECOORA was shallow water missions, using shallow gliders over deployments that were typically 2 to 4 weeks. We aimed for 4 weeks. We had some intentionally short missions, but since we're flying in shallow water, often 20 meters deep at the shallowest, and usually less than 150 meters, our deployment lengths are fairly short compared to some of the longer endurance missions in deeper water. So we did have one G1 that continuously sampled with science for around 38 days. We recovered on day 39. That was, I think, for most of us in our regional group, a record for a G1 on alkalines. Kind of fun. So we gathered 159 days through these successful deployments. Our focus in these shallow water deployments and in the region in general is on the edge of the Gulf Stream, which really is the defining feature of the South Atlantic bight. And then our other essential ocean feature that we track with our shallow water deployments is shelf stratification. In general, shelf TS characteristics aren't captured very well by climatology. It's not unusual for climatology to be several degrees and 1 or 2 salinity units from what we measure on many parts of the shelf. So we're getting valuable data for data assimilation into models. We had several Navy glider deployments, one shallow water deployment that was ill-fated. We should have known in advance that Navy glider 666 would not have a happy end. It went off radar after 13 days. But we do have 2 deep gliders that are actually still out there. They were deployed 175 kilometers offshore. 175 miles, I believe, offshore with the cyan lines out there, and they're running a track that we had coordinated with sail drone tracks in the Sargasso Sea. And then we played tagged and received NG645 after it came around the bend. Lastly, Robert Todd at Woods Hole ran 5 deployments that were funded through NOAA's GOMO program. These generally were deployed off of Miami and then went from the SAB into the Mid-Atlantic Bight and were recovered in the New England area. Next slide, please. So I want to talk a little bit about our collaboration with Sail Drone, with AOML and PMEL scientists who were leading the program there. We had 5 sail drones available for hurricane season as part of this project. 2 of them were assigned to the Southeast Atlantic. Sail drone 1040 was the one that we put in the shallow side of the Gulf Stream edge, and then SD 1031 was in the Sargasso Sea. We sent it to an NDBC buoy south of Hatteras, and then you can see it sail offshore, and then the glider and the sail drone attempted a track around the triangle. So the idea was to coordinate the motion of the sail drone with our gliders and collect co-located measurements between the 2 instruments. We had an opportunity for a lot of cross-calibration, which was particularly valuable. Calibrating the sail drones with the gliders. The lower left shows a picture of a calibration exercise we did at Gray's Reef, where the NOAA vessel Nancy Foster was operating for Gray's Reef near the NDBC buoy. So it was a quadruple threat of cross-calibration. We also calibrated near multiple buoys off of North Carolina. Overall, we learned a lot of lessons about piloting sail drones in the Gulf Stream. It's not straightforward in terms of thinking about wind coming from one direction, currents coming from another, and extensive changes in the wave field and the wind field across those gradients. The project overall, there were a lot of lessons learned about operating sail drones in strong wind conditions, actually with a modified sail, and about cross-platform coordination. You've got different vehicles moving at different speeds. And I'm not sure if it'll be in the Caribbean section or not, but the group working in the Caribbean caught a fantastic data set with sail drone 1045, which went into the eye of Hurricane Sam. It's fantastic science value, but also PR value. There's truly nauseating footage available on YouTube from video on board the sail drone, which I think really helps us translate the impact of our work. Overall, having science data from an ADCP and a glider and a sail drone really lets you put together the picture of why understanding subsurface density information is so important for understanding hurricanes. What are those connections between the ocean and the atmosphere, and measuring, being able to quantify air-sea interaction and fluxes. The question of air-sea interaction across the Gulf Stream gradients is an interesting science question on its own, regardless of hurricane season or not. But it also has an operational value in the data from the sail drone, the ADCP data, for example, will help us see where the currents are shifting, where the strongest gradients are, so that advises our glider operations and helps us be able to build strategies of cooperative navigation. Next slide, please. So my last little sort of highlight of the season is really a focus on optimizing the navigation, both on the SECOORA glider side and in the use of the Navy gliders. So on the upper two left plots show some output from a product we developed at from Skidaway and Georgia Tech called Genius, the Glider Environmental Network Information System, that basically takes input from the gliders and from operational or empirical ocean models to plan paths and optimize the navigation of the glider. So we can also use it, in addition to generating waypoints, we can use it to detect anomalies from the flight of the instrument. For example, detect if we lost a wing. The example shown here is changes in forward speed that we can detect because of the presence of a remora. On the lower left, there's an example of a quasi-automated tool we use that's MATLAB based. We described it in a recent webinar for UG2. When you're flying in and out of 2 meter per second currents, you swim out of it just like a riptide. Perpendicular to the strongest current. So we can generate a lot of waypoint lists automatically without as much brain power at 3 in the morning. And then the right-hand side of the slide shows some of our planning for Navy Glider 645 as it made its way around the bend of the loop current and around Miami. So we had a group of us, a small group of 4 or 5 of us who gathered weekly and made decisions about what goal positions we wanted the glider to take, keeping in mind the light yellow line shows the EEZs. And so there was a lot of strategy in looking at different models, which often pointed to different pictures of what was going on. And so we had to use satellite and glider data to figure out what we actually believed was happening, to advise what the goals might be for navigation. And so this is where GHOST came in super handy for us. It's the guidance of heterogeneous observation systems operated by Lucy Smedstad, Charlie Barron, and John Rogers-Catrone at NRL and NAVO. So the idea is to send a goal position and to use the Navy models to automatically build a set of waypoints. We also built in no-fly zones with the EEZs, so we wouldn't go dark in Cuban waters. So it was a really valuable exercise. We learned a lot about how and when to use these tools. So we're really grateful to them. Thank you.
Excellent. Thanks, Catherine. Great talk. So next we'll move into the Mid-Atlantic Bight area. We have Mike Crowley from Rutgers, and you can see his team with Scott Glenn, Travis Miles, Donglei Gong, Matt Oliver, Wendell Brown, Charlie Flagg, also contributing, as well as many other folks that do the work in the background as well. But turn it over to you, Mike. Thanks.
Thanks, Bill. As Bill said, Mike Crowley from Rutgers, part of MARACOOS, and that as that first slide shows, there's a lot of us, and there's two of the things we do a lot of are leveraging and collaboration between a lot of us that are operating gliders here in the MAB, and that's a big important piece for us. Right, Bill, next slide. So during hurricane seasons, that's June 1 to end of November, we had 41 gliders that were deployed. And these are numerous missions funded by state, federal, private groups. NSF, like OOI is a good example. You see that the maps to the right, the map to the right shows the different glider deployments that were made during this time frame. So the OOI you can see in just south of Martha's Vineyard, Nantucket, but then there's numerous other groups and projects that are operating within the region. We had 3 Navy gliders during this time frame, and during that time frame they operated for 135 days. Although 2 of them, one of them was still in the water, and one of them was just recovered a couple of weeks ago, and there'll be more on that in a moment. As I mentioned, leveraged and a community working together. There are 11 different funding groups that funded this work. So for us, some of the big events for us were Claudette, Elsa, Henri, and Ida. So Henri was a was one that came right up into Rhode Island. There were 2 deaths and about $500 million worth of damages. In the bottom right-hand corner of this picture, you can see HF radar field actually shows, you can see the center of the track of Ida, or I'm sorry, of Henri, compared to what the National Hurricane Center's track was, which was actually just to the east of the wave field. So that's the CORA HF radar field that you see there. And that track went right into Rhode Island. The other one that we had, there was what occurred with Henri as it approached. It weakened as it approached, and it's what we've learned now to see is that ahead of eye cooling before the eye approaches. There's mixing and cooling ahead of the eye. So there's that cold pool underneath, which is that essential feature in the Mid-Atlantic, not just for hurricanes, but for fisheries and water quality. And that cold pool subsurface helped to cool, came to surface before the eye and helped cool the surface, which weakened the ability of the hurricane as it approached the coast. Ida was different. Ida, as was mentioned earlier, hit Louisiana and then came up to the center of the country and then really wreaked some havoc on specifically the New York, New Jersey area. Like New York City experienced more than 3 inches of rain an hour. And for those in the Gulf thinking, well, okay, that's a pretty good amount of rain. But man, at New York City, there's no, it's impervious surface, right? It's falling down, and it really caused some issues in flooding. Throughout the U.S., there were 115 deaths and 75 billion in damages, and about 80% of those were experienced in Louisiana, New York, and New Jersey. It really was a different kind of storm coming to the middle part of the country and then really creating a mess as it exited back out into the ocean. We were able to this year to achieve simultaneous coverage of the MAB, shelf region, and the cold pool. The slides in the middle, those cross sections. Those cross sections were taken. If you look at the map, there's a little yellow arrow out of Atlantic City, New Jersey, going southeast toward the shelf. That's where that cross section occurred, and that was in mid to late July. The 8 days of cross section going out. What we're showing here, and there'll be more on this later. Our glider to RTOF's cross sections for salinity and temperature. Going back a couple of years, if you look at temperature, you can see RTOF's does pick up colder water at the subsurface in that shallow shelf. We're dealing, I think the deepest water there is maybe 85 meters or so to the right edge of those cross sections. And RTOF's never did a very good job in the shallow water of picking those up, and it does now. So it really is, it's picking up some of that cold pool, which is that in the glider temp, you see the black area. That largely is the cold pool, which is that very cold water that's there all summer long. We can see surface to bottom temperatures as high as differences as high as maybe 19, 20 degrees. In this instance, I think it's around 16 or so from temperature difference from top to bottom. So it's great to see that the RTOF's is improving on that end. But again, more on that a little later. It was the first collaborative effort with thanks to the Navy and the Slope Sea. We'll be a little bit more on that in a second too. A lot of communications, internal RAs, media, Navy, working on all of these different groups. Again, 41 gliders, 11 funding groups. We've added a few new partners this year as well. Stony Brook, Yukon, Hui, UMaine, I know they're a little further north, but we are working with them as well, and URI. So one of the really cool events, it's a good story, and it's the recovery of glider 738. So maybe go to the next slide, Bill, and then I'll introduce Dong Lai here. We had 2 Navy gliders out. You can see the tracks there, but we had 2 Navy gliders out from the fall up until, well, one is still in and one was recovered a couple weeks ago. And Dong Lai kind of spearheaded communications amongst numerous groups on recovery of 738. So Dong Lai, all yours.
All right, thanks, Mike. Just a bit of an update on these 2 Navy glider missions. So this is the first time that we're working with Navy deploying deep gliders into the slope C. And the idea was to really provide a long slope and cross slope sampling, capturing the not just the short-term storm event impact in that part of the ocean, but also capturing this seasonal change. So looking at the track, you can kind of tell in the middle that it didn't quite follow exactly a long slope and cross slope tracks. It was a very the Gulf Stream was close to the coast, closer to the coast than normal, and heavily influenced the flight of these two gliders. So we whether by design or not, we end up getting a lot of experience flying into and out of the Gulf Stream. So these gliders, both gliders flew well over 3 months. The collaboration include the Navy, NOAA, the National Science Foundation, academic partners at University of Delaware, VIMS, URI, Rutgers, and the piloting was done through the GOC and in collaboration with here at VIMS and Rutgers. So it was a lot of operational experience gained in addition to the science data that was, we really got a unprecedented, for the slope C, it's a very undersampled region. So we got quite a bit of new data across the seasonal transition, going from the stratified season into the well-mixed winter season. And we also captured many upper ocean variability, many events that drives upper ocean variability, high wind events, etc. So there's a lot of data. There's more analysis to be done. Just a quick story. So we are trying to recover. We were trying to recover NG738 until it lost its ability to steer and was drifting way offshore toward some of the seamounts like Atlantis 2. So we really didn't think that the chance of getting her back was very high, but through partnership and reaching out to colleagues, and we found that RV Endeavor was on her way to Bermuda, and the National Science Foundation generously let her deviate from her original mission plan and picked her up in, I think it was 10-foot seas. It was quite a recovery, and it was successful. Right now, we're waiting for her to get her back into the mainland. For NG657, right now it's right off our coast of the Slope Sea, and we were going to go pick her up on Monday, and we have the VIMS Bay Eagle ready to go, and then it blew its weight today. The voltage dropped too low, and it's right now sitting inside the Gulf Stream, so it's getting affected pretty quickly offshore. So we are looking for all vessels and all parties with ability to recover a glider sometime within the next week. So if you have that capacity or know anyone, feel free to reach out. The Navy is looking. We reach out to Coast Guard and academic partners, and we'll probably reach out to commercial folks too. So this is a rapidly evolving situation, and without partnership, without help from everyone working together, these missions will not be successful. So thank you.
I will say, Don, like the story from 738, there was probably 5 or 6 days where we thought it's gone. It's probably heading east and it's not coming back. And you see the path in the orange there, and it was in a Gulf Stream meander, and they were able to get control of it again, and it got into an eddy. That's kind of as it hits back toward the northwest. It's on the southwestern side of a Gulf Stream, an old ring, and then they were able to get it back closer to the line where the Endeavor came in. And Dong Lai deserves a lot of credit. There was a lot of phone calls, a lot of time with a lot of different people. And was able to successfully get the Endeavor out there. So well done. Now we got to see what we can do with 657. Get another successful story.
Yeah, and thanks to the GOC for Navy for letting us use these two gliders, and it's been a really nice collaboration with them. All right.
Well, all right, we're done, Bill.
Okay. Next slide. Thank you very much, Mike and Dunlai. Just highlighting how the glider operations can change very rapidly and how important the collaboration and the efforts are. So fingers crossed we can get that other Navy glider for sure. Thanks. Okay, we moved down to our fourth regional area, IAS regional area down in the Caribbean here. We have, I believe, Dr. Patricia Chardon Maldonado from University of Puerto Rico, and Dr. Doug Wilson and Dr. Gustavo from that will lead the talks. So I turn it over to you, Patricia. Or is it Gustavo?
Hi, everyone.
Hey.
Yeah, I will start. Thank you. Hi, everyone.
Yes, hello. I will start, Bill, and to save bandwidth, which is not good today at home, I will get rid of my. You don't need to look at me. That's what I mean. Thank you. And you can hear me, right?
Yes.
Thank you very much. So thank you, Bill, and Bill for inviting me to be part of this presentation, and also to Patricia, and with whom I will share this presentation. The work that we will be showing is in the Caribbean Sea and Tropical Atlantic region, and involves a large group of institutions, from government to academic institutions, and also involves what we do, end-to-end work from engineering aspects, field operations, data management, and research. And if we go to the next slide, that probably I'm referring to that one now. Thank you. Great. And so from research, let me get rid of my tab there. Okay, great. Thank you. From research, what we know is that the main features that we have to monitor in the Caribbean Sea and the Tropical Atlantic is what you see there circling in red, and which are linked to hurricane intensity changes. Besides the SSTs, they are barrier layers, warm eddies, warm pools of waters. Barrier layers, if you are not familiar with the term, is when you have very low salinity with warm water at the top, and creates very stable layers, very warm, stable layers at the top, that even if you have winds that are trying to mix those warm waters with underneath waters, they cannot. So the water, regardless of what you have on top, the water will be always warm. And also the influx of warm water through the Antilles and the passages there. And all of this is, these are the features that we monitor at different spatial and time scales, and that have been adapted as our knowledge also changes. And curiously enough, we have adapted, like everybody else, as the budget changes. So, but we are fortunate that that represented for us an increase in transects. That is what you will see now, and those are the institutions that you see there that participate in these operations, the logo of the institutions. The next one, please. And there. And we started our operations in 2014. And we use sea gliders, mostly sea gliders in the region. When it comes to Navy gliders, they are Slocum and Rutgers 2, are Slocum, and this is these efforts are funded by supplemental funds. In year 2014, that is the these are the transects that you see there, the maps with the transects, and it starts at the top left. 2014, we only have 2 gliders, and so this year we completed our 8th hurricane season of observations, and we have observed survey ocean conditions during the passage of more than 30 tropical cyclones. And this map only shows the trajectories that we do between CARICOOS, OCOVI, and AMOL. OCOVI is a subgroup of CARICOOS. And An average mission that you see there, we went to having 8 gliders in the region. Last year, yeah, that's what we had, 8 gliders. Our missions are typically from 90 to 120 days. We spend more than 1,000 days at sea. And we're always glad to, fortunate to mention that we haven't, in all these missions that we have 60 missions already, more than 60 missions, we haven't lost one single glider yet. And that is thanks to the good work done by the engineers and by the deployment and recovery cruises. And so you see that we do mostly repeated transects. If you look at what we do, they repeat every year because we are oceanographers and we like to repeat transects. So not only to monitor these features and where they go, but also to see how the upper ocean thermal and salinity structure changes with time. That can also give us also, together with altimetry data and Argo observations, indications of what we already know, that the region is warming up. So the original AMOL CARICOOS partnerships grow to include Cape Eleuthera Institute in the Bahamas, the US Navy, OCOV in the Virgin Islands, Rutgers, the ANAMAR government agency in the Dominican Republic. And we all work alongside numerical modelers, including EMC and the at NOAA and AMOL and Rutgers University. We go to the next one, and I only have 5 slides, so 2 more. Thank you. We have many highlights, and so I will show you only a couple of them, and Patricia will show you the rest. You see 2 columns there with panels that are temperature to the left and salinity to the right. We use gliders, for example, to assess ocean operational models, RTOF in this case. And the difference are in the bottom panels. And what you see is RTOF, the no operational model, minus the actual glider observations. And if you look at the top, in the top part of the differences, you will see the RTOF is cooler, and RTOF is also has less salinity, a larger salinity. And what does this mean? It means that if a couple model represents fluxes correctly, then these 2 differences in representing the upper ocean will also consistently conduct to weaker tropical cyclone forecast. So we are using models and working with the modeling community to help also correct the physics of the models, because currently they are too cold and too salty, and that leads to less intensity in the storms if you get the fluxes correct. And then the 4th slide shows another highlight. It was mentioned already by Catherine in the Southeast US region, and AMOL, CARICOOS, and OCOV participated in collecting collocated and simultaneous observations with cell drones. The cell drones, as Catherine said, measure a suite of atmospheric and surface ocean parameters, and this allows to better estimate the enthalpy fluxes. One of the ultimate plans to conduct observations for NOAA would be to conduct observations using autonomous vehicle, and that is what you see in the cartoon below. So this year, using gliders and cell drones in the Caribbean region, we surveyed with collocated observations Tropical Cyclone Fred, Grace, Peter, and Peter. And we consider that this was, for us, was a highlight because, as Catherine said, it will help us to better not only assess the ocean models, but also better estimate the fluxes. And the last slide that I wanted to show is the webpage that we have at AMOL. My apologies, Patricia. I should have included the CARICOOS, but I believe you do it. And what you see there at the top is the Ocean Viewer, where we present in near real time the location of our observational assets. And that is a screenshot when Tropical Cyclone Grace travel of Puerto Rico. And below, we use some of this glider data and other data to assess, to monitor the sea surface temperature, sea surface salinity, and upper ocean heat content. And that gives us a broad idea of where hurricanes could intensify. But the actual data that you use in the models is actually from gliders and Argo floats, and that is a structure that we are monitoring with this effort. So Patricia, thank you very much, and now Patricia will show the rest.
Thank you, Gustavo. Bill, if you can. Yeah. We wanted to point out that not only we deploy the gliders to help us understand better the role of the ocean in hurricane intensity, but we also have some mesoscale ocean dynamics with characteristic dimensions on the order of kilometers that have been found to play a major role in upper ocean steering and mixing. So the manifestation of this structure all around the U.S. Caribbean region have been found to influence the coastal and oceanic waters, impacting upper ocean hydrodynamics and biogeochemistry. So the Northeastern Caribbean, I'm showing here some images, experience the frequent occurrence of tropical cyclones traveling over mesoscale features with water mass property impacted the intrusion of continental river plumes by the Orinoco and the Amazon. Here on the left side, we present a satellite verified chlorophyll concentration to facilitate the visual interpretation of these mesoscale features and the intrusion of the continental river plumes to a region. We know that these oceanic features present a major challenge to be correctly represented in ocean and atmospheric models, especially using the tropical cyclone intensity forecast. So the sustained high resolution observation of upper ocean temperature and salinity from the gliders in our region since 2014 hurricane season, as Gustavo mentioned, we started back then, have been key to advance our understanding of these oceanic features and the role of them in hurricane intensity changes. If you can pass to the other slide, please. Here are just some data from 2 gliders from this hurricane season that we deployed, one in the north. Well, we deployed 2 in the North Atlantic, in the Atlantic Ocean, and 3 in the Caribbean Sea. This is from NOAA, AMOL, and CARICOOS collaboration. We also deploy others to Virgin Islands, one from collaboration with the Navy and with Rutgers. So these, just to show that the upper ocean dynamics and the vertical exchanges or motions associated with the oceanographic features play a key role in modulating heat flux and the development of these intensification weakening of tropical cyclones. So this intrusion of water can also, there's less salty water and warm waters that come into the region that the gliders were able to measure, form this ocean barrier layer that have been linked to the potential of cyclone intensification. I wanted to also present the data from the Virgin Islands that had the opportunity to have collocated measurements with sail drones, but I will leave Wilson to explain better this slide and also the data collected with Rutgers and glider.
Okay, thanks. I'm here, Patricia. I assume everyone can hear me. This is an example of an overflight between Navy Glider 644 and Sail Drone 1048, and we were lucky enough to work with NOAA and Sail Drone to get this co-located time series off of St. Thomas after the hurricane missions had ended. And the 2 pictures of the upper and lower on the left are 500-meter views of temperature on the top and salinity on the bottom, and especially in the salinity when you can see the semi-diurnal internal tides that really a strong feature in this area and occur right at that the bottom of that salinity lens. And so it was really interesting to be able to compare these glider pictures, which we've seen before, but this time we have the advantage of looking at the current velocity structure associated with those from the sail drone. And that's what the two pictures on the right are ADCP profiles from the sail drone during that same time period. So that was a really interesting dynamical data set that we were able to collect, and we look forward to doing some analysis of that. And as Patricia mentioned, looking at the dynamics of that barrier layer and its formation and its dissipation. And as we know, it impacts hurricane intensity. Next slide, I think. So yeah, this is, I'm going to do this. This is Rutgers University gliders in the U.S. Virgin Islands. So we also work with Rutgers in a project sponsored by the Vetlesen Foundation that's been sending gliders a little further east, so during hurricane season. So these are our sort of easternmost barrier on the in the tropical Atlantic. And so they're out during hurricane season. So they do serve as hurricane gliders. You know, the data goes into GTS. We're studying the essential ocean features in the area, and particularly the transport of freshwater and heat through some of the passages in the northeastern Caribbean. So this is an example of the data sets we collected in 2021. And those were interesting, as Gustavo mentioned. This is another international aspect of this. We were able to work in collaboration with British Virgin Islands, Anguilla, the Netherlands with St. Martin and Saba and other islands, and the French, Antilles, and Antigua and Barbuda. So more than half a dozen different clearances there went into effect, and we've been working with those groups in order to, you know, if you're going to work in the Eastern Caribbean, you've got to be able to work in some of these international waters. So this was a good example of that. Presently, we also were able to put ADCPs on these gliders, and so one of the studies that's going on with Travis and Joe Gradone, a graduate student at Rutgers, is developing using the gliders with the ADCPs to look at transport by water mass in this region, and that's a big plus, being able to mix those two together. So I think that's it for the Caribbean.
I have one more slide. Yeah.
Oh,
so
sorry, Patricia.
No worries. I want to highlight like all the efforts and the collaboration between the agencies, organizations, and institutions. So since 2014, or 8 years of hurricane season deployment, we have been able to sample 16 tropical cyclones that came close to Virginia and Puerto Rico. We collect around 62,000 temperature and salinity profiles, cover approximately 52,000 kilometers. And most important, we had the opportunity to train students and technical personnel on details of gliders operation. Next slide. Here, we just want you to show you some pictures of those moments that we were able to work with students and people that were helping us deploy the glider. So I think thanks to them, we were able to have a successful years of hurricane deployment. So thank you.
Excellent, thanks all. So we went across the 4 regions on the operational slide, the collection of the data, and the, you know, the importance of the data and the different types of features. We're going to go into the sort of the impact from the gliders as they get entered into the model. So we have Dr. Scott Glenn and Dr. Travis Miles from Rutgers, who's been doing some of this analysis, and we'll present it now. Thank you. I'll turn it over to you, Scott.
Thank you, Bill, Kathy. The group that works on this, Travis and I are there, but we meet weekly during the hurricane season. Kerri Whilden from TAMU is there. Mike Smith, Doug Wilson's there. Kathy and Bill join us also. And we're constantly looking at the operational models and how they're doing, especially after assimilating the data. And we can go to the next slide. And we've been doing this since about 2014, like the previous slide. We've been following the glider data into the models to see how the impact of that. And so here's the hurricane forecasting suite, the operational models that are in use today. The top row is the global models. These are the data simulative ocean forecast models. This is where that glider data eventually goes. And the Navy models there, first one, GOFS, the Global Ocean Forecast System, they're up to 3.1 on that one. We started with 3.0, and what an improvement it was to go to 3.1. So every year we see these improvements. GOFS used to be the initial condition for RTOFs, as we heard a couple of times already. RTOFs has now taken, RTOFs 2.0 has switched to assimilating the glider data itself. And so now that tie between the two models is cut, and they're kind of like independent runs now. Many of the same data sets go into them. And the third is the European Copernicus system. We often look at that one in our region. Also, it's used by people here. So now RTOFs 2.0 is that source for the initial condition. Our data simulation is much more closer to the regional coupled ocean atmosphere models in the bottom row. And the two operational models there are HWRF and HMON. They have different coupling, different oceans that are coupled into, but they all use the RTOFs initial condition. And then way over on the right is the HAVS, the experimental model. And there's so many different versions of this, but of course, one of them that we have a high interest in is where they do couple to RTOFs and some of the initial conditions, like for example, IDA for this year. The next slide. So those are the operational models, and the next slide shows the data flow. That white area in the middle is the data flow. So on one side, there are the glider operators, like the people on this UG2 call, and way over on the right-hand side are the models that we care about, where that data simulation is happening. And this is the data flow that goes in between these two. And up near the top, there's that OAR. The AOML has their own way to get into the GTS and get the data over there, but for the people in the UG2 community, they're more likely to be using the IUS glider DAC. And there's help to get you into the glider DAC and get that data onto the GTS. And so along this path, we've built many different ways to check the data as it's going through and do quality control and make sure everything that's supposed to be submitted is moving along as quickly as possible. So there's that IUS glider DAC on one side. You can view your gliders in that, see how it's doing in real time. And there's daily statistics that are generated that NOAA watches quite closely. Moving from the glider DAC, NDBC, so at the Weather Service, they submit the glider data to the GTS and the different NCIP data tanks. And they produce a daily message that you can sign up for and see how many profiles your glider were submitted to the GTS and how they did. From there, it goes into the NCIP data tanks, and then it's assimilated into the operational models, RTOFs in this case, and by the EMC, the Environmental Modeling Center. And they have a viewer that you can look, and you can look at your glider, where it is. You can look at the profiles, compare it to the models, and see the increments that are being used to help nudge the models in the right direction. And then what we do at the very end is we go back and we compare the two models, the Navy model and the RTOFs model, because they're kind of the same family, they're kind of siblings there, and see how they're doing and look for the differences, because they are slightly different implementations of very similar models. And so that glider flow begins with IUS on one side and ends with IUS looking at the impacts at the other. We do this region by region, weekly. We're summarizing these results. I'm just going to show a couple of the results here. We'll focus on the Gulf. We have some exciting results there, I think, with Hurricane Ida. So the next slide. Here is two versions of the temperature at 200 meters. RTOFs is on the left and GOFs, the Navy models, on the right. And the National Academy deployed a lot of Argo floats over the last couple of years, and the Gulf has seen the benefit of this. And so the dots that you see on that map, those are a lot of Argo floats, and the lines are the gliders. And so that in situ data has a big impact on the assimilation in these models. And the two models, is anywhere you see like Argo and glider data, very good agreement between the two of those. The differences that occur are often in the data poorer regions where maybe it's just altimetry that you're assimilating. And so the big features that we're looking at here, this is at the beginning of August, is that loop current eddy, that warm water, and then the cold water that surrounds it. And you can see all the gliders are out. I mean, all the floats there in that deep water side. And that's an important realization right there, that the floats are going to be there in the deep water, and the gliders are covering a lot of the shallower inshore side of these features. Next slide, please. One of the important things is to get the vertical distribution of the temperature and salinity correct. And here's just an example plots from that glider on that realization on that day. And on the left is the temperature profiles, the right are the salinity profiles. And here we zoom into the top 400 meters. 400 meters is where we see most of the variations. You know, the gliders often go down to 1,000 meters and Argo is deeper, but here we can see a very common picture for what we see for temperature profiles now. Blue is the glider data, green is RTOFs, red is GOFs, and you can hardly see the difference between them. And the Europeans is, you know, are kind of like that outlier in temperature. And so over and over again, tremendous progress in getting the temperature profiles. You know, we do see differences at times, especially when there is not data available from the profilers, either Argo or the gliders. But when that data is there, these models seem to agree quite well with the data and with each other. On the right is the salinity profiles. There you see some of the challenges, and here's like the subsurface salinity peak. Everybody's having troubles with that. Another is the barrier layers that you get at the surface. And so that's another problem area. So salinity is that challenge now that we're trying to focus on, trying to get the salinities right. The next slide, please. And so, like, how widespread is that issue of the surface salinity? So here's a map of surface salinity in the Gulf from the two models that we see. And this is where we see like bigger differences between those two models. And we just saw Gustavo say that that RTOS was saltier than the data in the Caribbean. Well, here RTOS is the fresher of the models. And so this is some of the differences we see now. Big differences in the boundary layer, in the barrier layers at the surface. And the question is, what impact does this have? And so one of the important tests that occurred this year was during Hurricane Ida. And so the next slide, please. Here's Hurricane Ida. It's south of Cuba. It's about 2 days before landfall, a little bit more than 2 days. And at this point, all the forecast tracks kind of locked on and really were corresponding to this, this landfall in Louisiana. There was still quite a bit of variability in the intensity, but HWARF was coming on strong, showing it was going to be a major hurricane, well in advance. And so that was the forecast that we were looking at. And on the right in the top diagram there, you see the temperature at 200 meters, and you see the hurricane coming up, intensifying as it goes over the loop current and that loop current eddy, but then really intensifying on the northern side of the eddy and as it's going over the shelf. So it's a lot happened in shallow water, intensifying the storm, not weakening the storm. And so a lot of the messages you might see from Weather Service. They might talk about the weakening that might occur as you hit in the coast. Here it intensified. And so why is it intensifying there? And if we look at the bottom plot on the right, we look at that barrier layer. And here was a very essential, we see that the blue water for the barrier layer that the glider's in. This was a really important task that TAMU, that Kerri Whilden did with the GOC, where all the Argo floats were on the warm side of the front. And so the two of them worked very hard to get this one glider that was out there on the cold side of the front, and on the freshwater side. And because they were able to do that, and we were able to compare to the models that were operational, we had a very good idea that, hey, H-Wharf has a pretty good ocean under it. We better start listening to it. Let's look at that comparison. That's the next slide. There's that temperature and salinity, those plots from the glider at the top and RTOFs at the bottom. That's that operational model. And so we see that the surface temperature is right. The depth of the black line is the depth of the 26-degree isotherm. It's right. It's even the global model is getting some of that cooling right as the storm passes. And the global models is not where we're looking to get the processes right. The processes are focused on the regional models. Here, we're just trying to get the initial condition right. But salinity has challenges. And so how important is that? That's one of the big questions. So the next slide, please. So here we did just one of the initial tests with a 1D mixing model, where on the left is the temperature profile and the salinity profile. And the salinity profile has that strong barrier layer in it that you see, where that very fresh surface water. And we just cut that off. Like if you had a regular TS curve to use for, instead of actually measured salinity. And so we did the 1D mixing model with the winds during that time to see how the temperature, the surface temperature varied with just 1D mixing. And that's the middle diagram on the right. And with the barrier layer is the blue line, and without the barrier layer is the red line. And see, without a barrier layer in that model, you get much more rapid cooling to a larger amount of cooling. You get the cooling focused ahead of the eye. And so you would get a much weaker storm than you would with the barrier layer there, which delays the cooling and doesn't allow as much to cool. If you look at the heat fluxes, the impact on the heat fluxes, you see that there's the difference in the latent heat and the sensible heat. So there's, with the barrier layer there, you get more heat going into the hurricane, up to about like 15% over the time when the hurricane's over there. And that's enough to impact intensity. And so as a result, with just a simple moving the glider over to the cold side, getting them both there, both on the warm and the cold side, getting these 1D models going, we've motivated the 3D modeling proposals that have gone to HFIP to look at how this is impacted by H-Wharf with RTOFs underneath it. The last is the summary slide. So our 2021 operational data simulative global models, they are much more realistic than we've ever had. And we've been looking at this since 2014, and they're really outpacing the Europeans. The second bullet, all those gliders and the Argo. So here's the black dots are the Argo, the red lines are the gliders. They're working together, and they're really pushing this uncertainty away from the initial conditions and into the processes, which are handled by the regional models. We have some known challenges with salinity, these freshwater barriers and subsurface peaks. The temperature profiles, where we don't have Argo or we don't have gliders, there's differences, usually due to how we're doing the altimetry assimilation. And then the transport through the passages. Seems like every time we look at the transport through the passages, the transport is often going in the wrong direction. So that's another challenge. So we welcome everybody's participation in the 2022 hurricane season. No matter what your glider is doing out there, it can contribute to the hurricanes just by by joining in and contributing your data to the IU's glider DAC. We'll see it at the other side and watch the impact for you. Thank you.
Thank you, Scott. That was excellent. You know, at the end of the day, operationally for this hurricane mission, it's all about the so what factor, and that's getting this information in the models and improving intensity forecasts. And I think it's been mentioned by all the regional briefs as well as Scott, that the importance of not just getting there's gliders that are specific to the hurricane mission, but a big part of the effort is what we call OMGs, or other mission gliders, that, you know, if you have gliders out there during the, you know, preseason or during the season, or we would more than welcome getting at least the temperature and salinity data into the DAC. We can set you up with that through John Kerfoot at Rutgers. And that's a big contribution as well, because spatially we need as much data as we can get, well, spatially and temporally. So please, if there's any opportunities out there with the community to put data into the, not only just for the hurricane mission, but other missions as well, but specifically we're just looking at the hurricane mission for this webinar. But yes, I appreciate that. I think first, Crowley, I want you to just go on to the Slack workspace so that we make sure we get, because we're running close on time. If you could just talk to that real quick, I appreciate it.
Absolutely. So just very quickly, we've created a UG2 Slack workspace as in lieu of the hotline that we had discussed when we first were initiating this group. So everyone who indicated that they would be willing to be part of the hotline will be invited to join the workspace following this webinar. So I'm just waiting to hit the send button. If other people want to join, feel free to shoot us an email or let Bill know, and we can make sure that you're in that space. Thanks. Thanks,
Crowley. I mentioned about dropping questions in the chat to the speakers. I don't see any. If there's any real quick, please, maybe at this point, if somebody wants to chime in, they don't have to drop it in the chat. Have a couple minutes. It was mentioned in the chat session, I had mentioned about the workshop, and the plan is for it to be in person only. Sorry, I was remiss in mentioning that, but that is the plan at this time. And given the scenario, hopefully with returning somewhat to a normal post-pandemic environment, this should work out well. But that keeps the cost down, and really the goal of the workshop is to have a lot of interaction and conversations, both on, you know, offline as well as online. So that is our intent for that. We're going to continue the webinars every 2 months. Please, if you have topics, send them to me. Again, this is for the group. It's not for me to dictate. And we're also looking for industry partners to continue with the industry briefs as well as we did during the last season. So please send me any ideas, and we'll consolidate those and put them into future webinars. Any, thank you. Yeah, going back to the glider that's in distress out there. Thanks, Captain Mowat. He just said a quick scrub of the NOAA ship shows nothing in the area of 657 in the next few weeks. So keep our fingers crossed that maybe there's some Navy vessels off of Norfolk operating out there. We'll continue to look for that. Any other quick closing remarks from anybody? Any questions for me or anything? We do record this, and we do put it on the website, underwatergliders.org, so you can always download it. And I just want to thank the speakers again. Super job. Lots of work that goes into that effort, and lots of collaboration and great talks. And I really appreciate it and look forward to some in the future. Thank you very much.